Okay, today I will talk about this question on the common prefix of case strings after removal. This question was present in today's context, so I decided to record a video to explain this to everyone that would like to understand how to solve this problem and also myself in the future. So will not read the problem because I'm assuming that you can pause the video and do it by yourself, or even you already did this in the contest. So summarizing here, the overall explanation would be you have a list of words and you want to answer this with an array with the same size. And in each step you will remove a word. Then you need to answer what is the biggest prefix that appears at least k times here. So in this case, which prefix we have? So we have the prefix r that appears here, appears 3 times, ru that appears 3 times, run that appears 2 times, j that appears 1 time, ju 1 time, jum 1 time, junt 1 time. So it's pretty clear for us that this one from the top, they are the candidates because they appear at least 2 times. So which one from these three is the biggest one? Run. And what is the length of run? Okay, so the length of run is 3, so we return to here. So for the next step, we're going to do the same thing again. So we will not have this element removed anymore. We actually will remove this one, and we will going to also count the frequency for the prefixes and everything. This will be a 4 because the longest prefix is junt, and it shows up twice. You see. So cut it to the chase. How we solve this problem? So if you have some experience, you probably notice that to do this, we're going to use some sort of trie. So trie is a very famous data structure that fits very well to this problem. So you're going to have a root, and each node after the root represents a letter. In this case, you have J, you have U, and you have M, and you're eventually going to have P. After that, you're going to also have R, E, U, and then and okay, now that you have this, you need to record the frequency of the letters that appear here. So J appears twice, so let's ignore this removal thing. Let's assume that we are going to send the raw inputs to the trie. So J appears twice, U twice, M twice, P twice, R appear 3, U 3, and 3. So if we know this, to know that which prefix appears with which frequency, we just need to store the prefixes that has frequency bigger than k and order them by the length. But we need to be careful here. We don't want to create copies for each prefix because this would be very expensive. So if you are using some language like C++, you can use string here. Or if you are in Golang, Golang provides a very nice string implementation where you don't need to form copies, you just manipulate pointers and interface this. So that will be my implementation here. So we'll do this. Of course, there is some ways you can do this without using string views and Go strings, but I believe that this makes the implementation way simple. So it's why I decided to implement this in Go for you guys. And to extend this to not using none of these two shouldn't be so that much hard. Anyways, so um, we're going to store the frequency, and whenever we have a prefix that exceeds the k, we're going to add this in some sort of data structure. And whether we add all the words, the word that we're going to remove, we're going to check this word has is the word with the biggest length. If it yes, we're going to check if the frequency is bigger than this one. If it's not, we're going to the second one, and so on and so forth. So it's going to be easier to understand once we start the implementation. But let's focus first on the tree, and we can go back to this solving part. So for implement the tree, we're going to have the struct tree. So the tree has a node, which is the root, and the node we're going to define here. Actually, I'm misleading with C++ declaration. Apologize. And each node has 26 pointers to child nodes. What else? We also store the frequency. That node was Walker. And we're going to have a constructor that will receive the words, the k. So here we're going to store the k as well. And we're going to have some sort of this. Try, see the try, so we provide the k, and we will pass the root as a node. Let's see if this works. I will return an empty array here just to check if my code actually compiles. Doesn't. Let's see why. For tire, try, and it's not used. Okay. We need to return pointer for this try. Turn as. Move forward. So what is the next step here? So we declare a try. We have the root. So we need to add the words. So for each word, we're going to do some sort of try, add word, and we return. So what is head word? So head word is a function um, that receives a word as an argument that is a string, and we have an iterator here to the root. So it's pretty classic try example. If you never do this, just search the internet. It's a very common algorithm. So we iterate inside of the words and to get the index of the child and check if it child's child index is new. I will assign this to a node. The frequency, I don't need to initialize this here. And I add here frequency plus plus. What else? So now the iterator received the child. Point to the next. And I guess this is the try part, like the implementation of the try itself. Let's see what's wrong here. I have a dot here. Has no fields childs. It's uppercase C, apologize. If I would have an autocomplete here, it would be way more easier. Unfortunately, I don't. Okay, it's funny. It's great. Yeah. So the try part, which is the easy part, is done. We need to now think in how can we return the words that has frequency bigger than k and the one with the biggest length. So what we can do, we can have some sort of hash map. So in this hash map, we would order the words based on the length. So the biggest words will be on the beginning and the smallest word will be on the end. And we would just this would be the key, of course, and the value would be the frequency. So if I have this, so if I have something like this, oh, this it's fun. And I will remove jump. Can basically reduce here. And I say, oh, jump has a frequency of 1. So I will go to the next one, which is run. And I see that run has a frequency of 3, which is fine. But this data structure will not be just, let's say, words itself. We're going to start actually all the prefixes. So it's a little bit expensive. So we would have also JU and P, 1 in this case, JU, J, and so on and so forth. So we will use some amount of memory, so it's why we have to use this if we go for this approach. So if you, I would use like say regular string copies in C++, um, we will exceed the amount of memory because every substring that you have will create another string. That's not very cool. So just to give you an idea, so if I have this in Golang, I cannot like C++. I can have some sort of custom comparator inside of the map, but in Golang we don't have this thing of ordered maps. So instead of having just a single map, I would need to have a map and an array. So that's the idea here. So the array will keep the strings ordered by the length, and the map will store the prefixes. If I only the array, I will end up with duplicated entries, and I don't want this because let's say if I will have two jumps, so jump will appear two times, J, U, and P will appear two times, and we don't want this. Just to clarify. So let's do it. Like having the prefixes frac map that will have the string, the integer and the key, the value, sorry. We're going to have also the prefixes array. Okay. So what we're going to do, we're going to check if um, if that prefix is not inside of the map, we're going to add it to the array. So what is the prefix here? So the prefix can be this, so it would be word starting from 0 to the I plus 1. So prefix here. So if prefix exists, so this would be the idle in Golang. Idle is like a common pattern specifically for this language. So this is how I check if an entry exists in the map. So if this is okay, this doesn't exist in the map, so it's not okay. I will add to the array. So it's the array name, and I need to do t dot prefix of the array, t dot prefix array, then t dot prefix array, prefix, and then I do t dot prefix map prefix receives frequency. Of course that I only want to do this if the frequency exceed k, so or equal at least. If this is bigger than or equal to k, I do the whole thing here. Otherwise, there is no point in doing this. Yeah, I think that's all. Let's see if this compiles. It doesn't. It's not compiling. Oh, I put a comma here. It should be a column. What else? Complain about the k. It's t k. Okay. Yeah, there we go. So now let's the solving part. So we will look through the words here, and we going need to check if the prefix that we have here, where actually I forgot, we need also to order the keys like the prefixes. So we're going to do this now. It's sort dot slices, and we pass the try dot prefix array. and we need to have an anonymous function here. I j that return a boolean. So if um, if fixed tree array at position I has a length different from the other one, we return the one that has bigger length. Otherwise, we return the one that is lexically bigger. And okay, moving back here. So now we need to check. Now we have the words ordered based on the length. And now we know that if we iterate inside of that prefix array, we're going to have uh, the, the first one that matches is the one that we're supposed to choose to the output. So talking about output, I will also declare this ends here in a proper way. So we will declare with the same size of the words. Moving back, so we're going to initialize our trie. So sorry if I forgot this. Select. Still trying this. So for each prefix inside trie.prefixes array, we go and check if this prefix is actually a prefix. So if word strings dot has prefix word prefix, and now we go into the map, which is prefix is freq map. Try prefix freq map prefix it's bigger than k. If that's the case, or prefix is bigger or equal to k, and it's not a prefix here. So if it's prefix and the frequency is bigger than k, so this would be equivalent to is bigger than -1 here. So I'm doing -1 because this one is a prefix. So since I'm removing this word, I need to decrement. So I'll just explain. And if it's not a prefix, if this is not a prefix, I don't need to decrement anything. So it's why I don't have the -1 or the just the bigger than here. I have big was equal. So this is a anyway. So in this situation, I will do as I see if the length of the prefix. So this is I, and I think that's it. I'm not sure if I forgot something. I forgot range, of course. Undefined sort, undefined, a lot of stuff. And here, and here. These cases. So on each one, I also have something. 60. This would be try. What's the thing here? White sort is undefined. Maybe sorts likes this? Yeah, seems to be that. Few more errors, so new map, so I forgot to initialize the map. So let's do this. So have the map here. Make string. Let me do outside. I never tried this. I'm not sure if this is possible. Fixes. Fix. Oh, actually, I forgot to add map. Yes. Okay. Yeah, we have an answer, but wasn't was I was planning. Huh. All ones? Why we have all ones? Am I incrementing the frequency? Yes, I am. Interesting. Let me maybe it's not ordering. That's possible. Let me just check this map. Yes, there is everything here, but I guess that's not ordered. Probably ordered. Let's see. Um, space. Interesting. Mm, maybe. Don't don't know. Oh, I forgot. I should break here. Okay. Yes. Let's see. Oh yes. So that's how we solve this problem. Apologize for the long video. The the trick here is to have a solid debate about tries and a little bit of creativity. Thanks for watching.